Our next speaker is Maria Gorinova, who's contributed a talk on efficient inference with discrete parameters in Stan.
Hello. Okay, hope you can hear me. Let me share screen.
And I will show up and give you a warning. You have 2 minutes left.
Sorry, this is for some reason being dodgy. Okay. Does this work?
Looks good. We were able to see your slides a minute ago.
Okay, I think this should be there we go. All right. Well, hello everybody. Nice. Firstly, it's really nice to be here. I thank you so much for organizing again. It was my favorite conference 2 years ago when it happened for the first time, and I'm really excited it's happening again. I'm very excited to be here. Okay, so today I'm going to be talking about some research that it really started from the question of how can we use program transformations to make programs, probabilistic programs, somehow more efficient to do discrete, to do inference in programs with discrete and continuous parameters simultaneously, and in particular how to do that in Stan. But obviously, a long time has passed since January when we submitted the abstract for this talk. So it grew to something that, in my opinion, can be applied to even more generally than that. And hopefully, there'll be time at the end to discuss this briefly. All right, so I'm not going to spend much time introducing Stan. I suppose most people have heard of it in the audience. It's one of the popular probabilistic programming languages out there and has amazing community and lots of support for all sorts of cool stuff. And partially, what makes Stan popular is the efficient MCMC algorithm it uses, which is a dynamic version of HMC. And this algorithm uses the gradient of the joint density described by the model in order to make inference more efficient. But now here, you can immediately probably see that this restricts right away the models we can express in Stan, and we can work with Stan, because we need, in order to be able to take the gradient of this joint density, we need it to be piecewise differentiable. And the immediate problem here is that this means that the parameters theta cannot be discrete, otherwise we can't take that gradient. But there exists a workaround, and this workaround is, it's well known. It's documented a lot in the Stan user guide and so on, where the user can use discrete parameters in Stan, kind of implicitly, by marginalizing them out of your program. And you can probably see where I'm going with this, which is that for this work, we decided we want to take a program that it's a Stan program, but with discrete parameters, and automatically apply this workaround in order to get regular Stan that we can then run HMC on. Right, and a side note here, actually in this talk, all the examples are not in Stan, but in Slick Stan, which is this blockless, more compositional version of Stan that we developed a couple of years ago, and it was actually presented at the previous proc. So, enough of this high-level stuff. Let's just dive into an example of how we can take a program with a discrete parameter and transform it using this workaround. Here we have a simple change point model where we are interested in modeling the point of change of the rate that certain event occurs at. So say that we have data, an array of data y, where we record the number of occurrences of certain events, say disasters, for each of many years, of t years. So you can imagine, like, depending on what we count as a disaster, that 2020 is like 1 gazillion disasters or something. And now we're going to model the number of disasters that appeared at year t as following a Poisson distribution, where the rate of this Poisson distribution is either E or L, depending on is this year t before or after the change point d. And d itself is a discrete parameter that we're interested in, together with E and L, which are continuous parameters. Okay, so this program we can't have in Stan, at least not written like that, because of this discrete parameter. But really, we can rewrite it in the following way. So firstly, what this program corresponds to a joint density, and this joint density is on the data y, on the continuous parameter ENL, parameter CNL, and the discrete parameter d, and it can be written as this. Now, to marginalize out d, we simply put a sum in front of this expression. So we sum over all possible values that d can take, which is from 1 to t, and that's it. And the way we're going to express this in terms of the program is quite straightforward. We're just going to wrap the program into a for loop, where we're going to loop over possible values for d, and kind of record this value at the particular EL and Y in some array ACC indexed by the value that d takes. So this body of the loop, of the for loop, corresponds to this bit, the inner bit of the sum. And then all we have to do once we compute this is that we're going to add an undirected factor, and this is the way we add an undirected factor in stan/slickstan, which sums over the values over the array ACC. Okay, and I mean, here you can see like tiny bits such as oh well, like these two factors P and PL don't really depend on these, so we can take them out of the sum. So we can do that by just pushing some of the statements outside and stuff like that. So okay, we can do tiny optimizations like that. So this is the overall picture on the same slide. We started from this program, which has a discrete parameter, and it defines the density over y, e, l, and d. Then we summed out d from this by just having a simple for loop. And then the interesting bit here is that this ACC actually contains a normalized version of the probability of d given the rest of the variables. So we can normalize this and actually then use a simple random number generator to sample d again. So not only so what we managed to do here is that we marginalized out d, so now we can plug in this bit of the program into HMC to sample E and L given the data y. And now that we've done that, we also have computed this ACC array that allows us to then resample the given this information afterwards. So that seems, relatively straightforward. All we have to do is just wrap our entire program into arrays. That's it, like whatever. But would that work? What if we have more variables? So more discrete variables. So for every discrete variable, we will have to put an extra sum, right? We will have some per variable. So this means, one, that this array ACC where we would accumulate things is n-dimensional. And two, we're going to have n-nested for loops. So obviously this doesn't scale. But it's not going to scale in the general case. Like if we take a general graph, it's not going to work. But for many problems in practice, we have kind of loosely dependent structure of variables. So one very famous example is hidden Markov models, where each variable only depends on the previous and the next variable, or is only connected to the previous and the next variable in the chain. And in situations like that, we can actually do these sums in pairs. And by doing them, so taking here just the last and the second to last variables and kind of doing this bit of the computation first and then propagating this. So by doing this pairing and computing it separately, we can actually make this much more efficient. And instead of, so here we have n nested for loops, well, here we can have n two nested for loops. So they're going to be like pairs of two nested for loops and of those right after the other. Okay, so there is actually a general way of doing this, and this general way is nothing new. Again, very well-known algorithm called variable elimination. And this, I'm just going to go quickly through it so we're on the same page. It's quite simple. We have a factor graph that represents our program like that. And then in order to eliminate one of the variables, say Z1, what we're going to do is we're just going to take Z1. We're going to take all the factors that neighbor Z1. We're going to remove them from the graph. And instead, we're going to add a new factor that is the sum over Z1 of the product of these three previous factors that we had here, right? So this is their product. And we're going to connect this new factor to whatever neighbors Z1 had. And that's it. And now Z1 is eliminated from this graph. And we can do this because we know that all these other factors don't depend on Z1. And now if we want to eliminate Z2, we do the same thing. We take Z2, we take all the neighboring factors, we sum them out, and we add a new factor representing this. Okay, so what's the problem? I mean, right, so the transformation is quite simple. We just like sum out variables from the program with for loops. The algorithm for doing this efficiently is quite simple. It's just variable elimination. It has been known for ages, nothing new. But what it requires is that we need to, so in all of that, we had an explicit factor graph. And we knew exactly what these factors are, and we can play with them. We can recompute them, we can compute new factors, and so on. Well, when we have a program, things are not that obvious. So going back to the change point model, if we just add a couple of, nonsense lines here, suddenly the factors that neighbor our discrete variable D are scattered around. So here we have A that's computed from D, and then we use A in the likelihood term. But then there is some other expressions in the middle that completely don't depend on this. So how do we given that we want to rewrite the program, how do we efficiently, one, figure out which discrete variable depends on which discrete variable, and two, figure out what statements we should separate out in order and put them into their respective for loops in order to do this marginalization efficiently and correctly. And that brings me to the key idea of our work, which was to so it has two stages. One is to use information flow analysis and type inference to analyze the conditional independence relationships in the program. So kind of analyze this and figure out that here Z3 is conditionally independent on Z1 given Z2, for example. So that kind of relationships. And then using those conditional independence relationships and kind of assigning something to each variable in the program, we can actually slice our program into several different sections, and so that we can reorganize it to do this marginalization efficiently. And I think I have a little bit of time to go into this
Just
slightly.
a couple minutes, but yes.
Okay, awesome. So I don't need more than a couple of minutes, so that's perfect. So roughly how this works, and if you're interested into more details, please come to the poster session later. Roughly how it works is that we are going to assign level types to each variable in our program. So what's that? So in information flow, we want to analyze how the information flows within the program between variables. So these level types, they kind of say they kind of express this hierarchy in our program. And we have 3 of them here, and they form what's called a semilattice, where there is a relationship defined between L1 and L2 and L1 and L3, but there isn't any between L2 and L3, right? So what this means is that when we, by assigning particular types to variables in our program and then inferring the rest of those types of these level types, we can actually separate out groups of statements that don't depend on other groups of statements. So what we're going to do here is that we're going to say that all our continuous parameters in the program are of level L1, and we're going to say that the variable that we want to eliminate is of level L2. Now we infer all the other types in the program. So, like if we have a complicated program, maybe I should show this one. If we have a program like that, we're going to, for example, we're going to infer that the type of the variable A is L2 because it depends on D, which is L2. So the information kind of like flows in that direction. So we know that it's L2. This is roughly the idea. And now having done that, we can slice the program based on these 3 levels. And what we're going to get is 3 bits of program. So here S1, S2, and S3 are just bits of program, such that this bit of program is completely separated from this bit of program. And that's, again, because there is no relationship defined between the L2 and the L3 variables. So they're completely separated through L1. In other words, the L3 variables are conditionally independent on the L2 variables given the L1 variables. And expressing it as a factor graph like that is very clear how we're going to, what we have to do to eliminate XL2, which is what we set to our discrete parameter of choice. We just have to do variable elimination on this bit, right? So we know which bit of program to plug there. And that allows us to deal with programs with more complicated control flow and so on. So yeah, we can talk more about this at the poster session, but for now, I am happy to take any questions. And also, just quick mention, the paper describing this is now on arXiv. It's called Conditional Independence by Typing. Please check it out if you're interested. And also, Slickspan is finally open source. So please also check this out. Thanks.
Thank you for the wonderful talk. One question with a lot of votes from the audience is, have you considered discrete random variables with infinite support? And I'd be interested in hearing either or both your perspective on their utility in this setting, and also the technical challenges involved in supporting them.
Yeah, that's a very good question. Thank you for whoever asked that. Yes, we cannot do discrete variables with infinite support this way. There might be some way to do it approximately, but we haven't really looked into this. The way it's described right now, we can't do it. But all the conditional independence stuff still works, right? So that's actually relating to what I said in the beginning. This conditional independence relationship and ways of determining conditional independence, that is the more general conclusion we reach, that actually we can take that and use it for many applications. It doesn't have to be these discrete variable elimination things. So that's fine. But yeah, the elimination doesn't work with infinite support.
Thank you again.